In this video we'll see the analysis of differential amplifier for a common input. So let us write the differential amplifier with resistive loads. So this is my differential amplifier with a tail current source I. So this is minus VSS, this is VDD, and then let me write this is V in 2, let us write as V in 1. So this is V01, this is V02. Let me write this. Let us always consider for the first analysis it has the matched transistors, so matched resistors also. This is M1, M2, so this is the NMOS transistor, and this is. And let us now consider an input voltage which is common to both of them. You can see I'm applying a input voltage which may call it as VC. Okay, VCM is a common mode voltage. Now, even before applying this AC signal, this is a small signal AC signal. So before I apply this AC signal, so there was a DC current ID1 and there is a DC current ID2 flowing in both the transistor, that is M1 and M2. Because of the matched pair of M1, M2 and the RDs are same, the value of ID1 is equal to ID2 and will be equal to half of the tail current, So this is the values of the DC current that is flowing through M1 and M2, and we know that these DC current will decide what is the value of transconductance. So GM we know that is equal to under root of 2ID Kp W by L. Suppose if you are looking for GM1, then this becomes ID1 and this becomes W by L1. So since we are assuming ID1 is equal to ID2 is equal to I by 2, so then I can write GM1 is equal to GM2 is equal to GM, and it is equal to the root of 2 into ID1 or ID2. I can write it as simply I by 2. I can write it as I by 2 Kp W by L. So W by L is common for both of them, whatever the value that you are taking. So this GM will be given in terms of the tail current magnitude, the Kp value, and W by L, which is common for both the transistor. This is the value of GM, that is that is the transconductance of each of the transistor. Okay, with this GM, if I apply a signal, this is VCM, that is an input voltage V in 1 as well as V in 2. The same input voltage of VCM is applied to both input 1 as well as input 2. So we know that for any MOSFET, if you are applying VCM or any small signal voltage, we will end up with a small signal current which is given by VGS. Of course, let me just write the equivalent circuit of the AC equivalent circuit of a MOSFET without the value of lambda. With lambda equal to 0, then R0 becomes infinity. So this is GM into VGS. This is the value of ID what we are looking at. This is VGS. Now this is gate, source and drain. Between drain to source, that is from drain to source, I won't have a current small ID, which is the DC current. That DC current will be given by VGS into GM. In this case, VGS is actually the VCM. So I can write it as VCM is equal to your VGS, or VGS is equal to VCM. So from which I can write ID is equal to the small signal voltage multiplied by the transconductance of the transistor. This is the value of ID which is flowing through both the transistor. You can see now this is the DC current. Along with the DC current, there is a small AC current is also flowing, that is small ID. There is a small ID flowing in both of them. Magnitude of that small signal current is VCM into GM, it is same in both the cases. Now, in the previous video, while analyzing the differential amplifier for differential inputs, we considered this current source without a resistor and with resistor. So let us consider a resistor of RSS, which is typically present there across a current source of I. So let us consider this is RSS. Since we know that, okay, in the previous case, we certainly found that there was no impact of this RSS on the gain of your amplifier because it was a differentially applied input voltage and we were getting a 0 voltage here. There was a virtual ground for a differentially applied input voltage. Let us see, does the same analysis exist here for a common input or not, because we know that the same voltage is applied to this point as well as this point. We have a current that is flowing here in this direction, we have a current that is flowing here in this direction. Because you can see the direction of flow of current is in the same direction, now these two current have to certainly flow through this particular RSS. So this has to flow through this RSS. But in case of your differential input voltage, so as we discussed in the previous differential amplifier, we can see since the applied voltages were out of phase, the current was actually going back into your M2. This was the direction of flow. There was no current flowing. The DC current that was flowing here was actually 0. There was no current flowing through this RSS. The voltage drop was 0. So that's why we could able to write 0 volt, because there is an open circuit and there is no drop happening here. So this was treated like open circuit for AC signal, But in this case, since the direction of current is same here, you cannot treat, of course since there is some amount of current flowing through this, you will certainly have some voltage over here, which is the AC voltage. Now if I want to write the AC analysis for this one, so now we know that all DC voltages, I will replace it by ground here. This is, I will replace that current source by open circuit. You can see this is now again ground. You have okay, RSS as the resistance, and then you have again one more RD. This is how it is going. Then you have the same voltage being applied. This is what? VCM. This is RD. This is again RD. This is V01, V02. See now, because of this applied voltage VCM, so there is a current which is flowing here, which is ID. Because of the same voltage is applied here, this is also NMOS transistor, you have a current ID. Since all these two currents will just merge and then it will pass through this, the AC voltage at this point is a non-zero value. So you cannot consider virtual ground. Virtual ground is ruled out in this common voltage. So if you are applying a common voltage, this virtual ground is not there for common input voltage. So for common input voltages, there is no virtual ground because there is some drop happening. But in case of differential input voltage, so there was a concept of virtual ground because there was no voltage flowing here, and this was AC ground and there was no drop. You virtually had it as a 0 volt. Since it is not 0 volt, so in order to analyze this, so we need to totally have it in a totally different way. So what we'll do is to analyze the gain of this particular differential amplifier for a common input voltage, let us divide this entire circuit into two halves. So let me just put a vertical line here. When I put a vertical line, okay, I can just put this RSS over here. So what I'll do, I'll put the RSS here. When I put a vertical line, you can see there is a RD, there's a M1 transistor. So there is a RD, there is a M1 transistor, there is again same RD, there's a M2 transistor. We know that M1 and M2 are identical, and we have a resistor RSS which is common to both of them, and we have the input voltage VCM, the same input voltage is applied here also. So what I can write this as, instead of having a single circuit and then struggling to get what is V01 and V02, let us split this circuit into two exact halves and try to analyze it. So what I'll do, I will retain this part as it is. So I'm retaining, this is my RD, this is ground, this is M1. You can see this is my VCM, and I will write the other part also. So this is ground, I will write this as my RD. So this is V01, this is V02. I will write this is my M2. Because the same input voltage applied, let me write VCM here. You can see this resistor is the one which is, of course, let me just take out this resistor. This is the resistor which needs to be split now. So what I'll do, I will split this resistor into two parts such that the effect of these two upon merging will have the same value. Assume that you have a resistor RSS has to be represented by two resistors, so that whenever you combine them it should be again the same. So we know that I can split a resistor RSS into two parts such that upon merging it should again end up with RSS. Suppose if you have it as 2 RSS and 2 RSS, upon merging, because two resistors of 2 RSS and 2 RSS, if they are connected in parallel, it will become exactly RSS. So I will take the value of this as 2 RSS and take the value of this as 2 RSS. You can see this is input voltage, this is output voltage, this is input voltage, this is output voltage. Now we have two different amplifiers. So now does this resemble any particular amplifier? So let me just see one CS amplifier. So how does a CS amplifier look like? This is how, this is my input voltage, this is, okay, let me write the AC equivalent of that. This is V0, this is RD. Is this a CS amplifier? This is a CS amplifier. So do we have a CS amplifier with a source degeneration? So we know that this is CS amplifier with source degeneration. Of course, this is my V in, this is my V0, this is AC ground, this is again AC ground. Okay, what was the gain of this? So we know that the gain of this is minus GM into RD, which is V0 by V in for a CS amplifier. CS amplifier with source degeneration, we know that its gain, that is V0 by V in, is equal to minus GM into RD by 1 plus GM into RS, or it was given by minus RD by 1 over GM plus RS. This was what? V0 by V in for a CS amplifier with source degeneration. So this is the expression for gain for an amplifier of this sort. Just resemble these two, or these two amplifiers are identically same. See here, there is a RD, there is a RD here. There is an input voltage, there is an input voltage VCM. There is a RSS, sorry, there is a RS source resistance. That source resistance you have it as 2 RSS, because this RSS which was there across the current source has been split into two different resistance to make a symmetry of that analysis of that circuit for analysis purpose. Now we have a differential amplifier with source degeneration. We have one more differential amplifier, sorry, one CS amplifier with source degeneration, one more CS amplifier with source degeneration. So now using this expression I can write V0 1 by VCM, which is nothing but the gain of a CS amplifier over here with, of course, source degeneration. Can I write it as RD by 1 over GM plus 2 RSS? Is it not exactly on these lines? In place of course it is negative. Can you see this is minus RD, same as RD here, because this RD we are assuming it will be same, of course the naming at least. Can you see this GM, we are assuming the transconductance of this transistor as GM, and only thing is that in place of RS I have a 2 RSS. to RSS. So if you see here, this is what is V01 by VCM. This is single-ended gain of this differential amplifier for a common input. Because does this V01 represent this V01? Because these two are exactly identical. These two are exactly identical because we just made a split of this RSS. These two are exactly same. If I'm measuring V01 by VCM, even though it is said to be the gain of a CS amplifier with source degeneration, which is exactly the single-ended gain of differential amplifier with common input. So we have two single-ended gains, that is V01 by VCM as equal to minus RD by 1 over GM plus 2 RSS. This is for V01 by VCM. How about this V02 by VCM? That is also exactly same. So what I'll have, V02 by VCM is also equal to minus RD by 1 over GM plus 2 RSS. Hardly there is no difference between V01 by VCM and V02 by VCM. I will write it as ACS. This is again ACS. AC stands for gain of the amplifier in common mode with single ended. Gain of the amplifier with common mode with single ended is so and so. If at all, if you want to find out what is V02 minus V01 by VCM, this is what I'm interested in. V02 minus V01 by VCM, which is nothing but you are measuring the output voltage not single-ended, but you are measuring a differential output voltage. I want to measure a differential output voltage. So this is V02 minus V01 divided by VCM. So I just want to measure it here like this. It is plus minus with respect to VCM. So in such case, so as we know that this is exactly equal to V02 by VCM minus V01 by VCM. So what is V02 by VCM? It is this value. What is minus of V01 by VCM? It is the same value. Since it is minus of minus, this will actually become equal to 0. So what is the meaning of this 0 is, if you apply a common voltage to a differential amplifier, you will certainly have some single-ended gain, but the differential gain of this amplifier for a common input voltage is 0, meaning that if at all, if you have any common signal, if you are measuring the output voltage in differential mode, the output voltage is 0, meaning it rejects the common signal if you are measuring it differentially. So this 0 actually means it is rejecting the common signal. This whatever VCM signal you apply, if you measure the voltages differentially, the output voltage is 0. So let us go to this LT spice and try to examine the same thing. So what I'll do is, let me just apply a common signal. So what I'll do, I will delete this and I will make the same voltage here. I will make this input 1 and input 2 both as, okay, maybe let me just run through like this. Now be careful, there should not be any node created here. You can see the same input voltage is applied to both of them. Let me just now you can see I should have a value of RSS. So if you don't have a value of RSS, the analysis cannot be done, because in this case we have certainly considered this RSS. Without considering this RSS, I cannot write this expression. So while analyzing the differential amplifier, for common input, please have this RSS which is coming out to be across the current source. So let me again go back to this schematic. So I have this. Now if I measure V01, this happens to be the single-ended gain of this amplifier with a common input. Again, this is also single-ended output, and if I make V02 minus V01, that will become differential output voltage. So if I, of course, we know the value of GM and all those things. Okay, let us do it once. Let me run this. If I run it now, let me just measure what is the input voltage. So this is my input voltage. This is now VCM. VCM is a common voltage which is applied to both the inputs. Let me measure what is V02. Sorry, V01. V01 is actually, as per this, V01 is what is V01? V01 is VCM multiplied by minus RD into 1 over GM plus 2 RSS. This is the expression for, this is the value of the output voltage at V01. Let me go back and try to see. This is my okay, you cannot see anything over there. What I'll do is I'll just make it in different panes. We can see the difference. Now you can see actually there is nothing is visible. Let me put it into different pane and try to see. Can you see it is visible? Why it was not visible is because you can see the peak to peak amplitude is so less. Peak to peak amplitude of this is so less. So while measuring the single-ended voltage of this common mode, please put it in different panes. If you put it in the same pane, you will find it, okay, there is no output waveform, but there is an output waveform. See now, this is V01. Let me just have a different color for this. Now this is the output voltage. Again, this is centered around 400 millivolt as we discussed in the previous case. Now why it is centered around 400 is, let me again just go back to my camera and then show you. So you have this is at 0.9 volt, and this is, of course, you have a current of 500 microampere flowing here, and you have 1 kilo ohm. The drop is 500 millivolt. At this point you will have 0.4 volt, and you are applying a VCM here. There is a VCM here, and there is a 2 RSS effectively, and you are looking for, this is 0 centered around 0.4 volt. You will have, if the input voltage is applied in this direction, that is, if it is going high, the output voltage will actually go in the opposite direction. The output voltage actually go in the opposite direction. The gain of this happens to be minus RD divided by 1 over GM plus 2 RSS. So as we discussed in the previous video, the value of GMA is 1.41 millisiemens. The value of RD we considered is 1K. The value of RSS, that what we are hearing, is 100K. So by substituting all these values, if you find what is gain of the amplifier in common mode when you are measuring single-ended is equal to, let us actually predict what is the gain and then verify what is the gain. It is now of course it is minus of 1 exponential 3 divided by, it is 1.41 exponential minus 3 whole inverse. Okay, sorry, let me just, it is exponential minus 3 whole inverse plus 200k, 200 exponential 3. So if you can actually see, the gain of this amplifier happens to be 4.98 millivolt per volt. This is the gain of the amplifier, meaning if this is the gain of the amplifier, so what is ACS? How do you verify it? It is V01 by VCM. It should be equal to minus 4.98 milli. If you want to know what is V01, V01 is actually minus 4.98 milli multiplied by VCM. Since we have a VCM of 200 millivolt peak to peak, let me just do it for V01 peak to peak is equal to minus 4.98 milli multiplied by VCM peak to peak. Since I know that VCM is 100 millivolt, this will be 200 millivolt multiplied by minus 4.98. So I'll just make it is 4.98 milli multiplied by, I will make it 200 because I'm looking at peak to peak. You can see it is now it should be 200 milli. So into 1 exponential minus 3 is actually suppose if I do this, it is actually 0.99 millivolt. So I should get V01 peak to peak should be so less. V01 peak to peak should be so less. So that's why you can see it's almost close to 1 millivolt. Let me go here and then try to see. This is my VCM. VCM peak to peak is 200 millivolt. That's what we applied. See here, this is almost 200 millivolt. Then what is V01 peak to peak? Can you see this is almost 994 microvolt, which is equal to 1 millivolt. That's what we are supposed to get, that value. Can you see here? We are supposed to get 0.99 millivolt means 999 microvolt. So that's what you're getting. So the gain of the amplifier is so less that the output voltage will be very less. So that's why the output voltage here is input multiplied by the gain. Since the gain itself is minus 4.98 milli, you are getting a very small output voltage peak to peak. Here you can see it is 200 millivolt peak to peak. Here it's hardly 1 millivolt peak to peak. So it's almost like, okay, it is rejecting fully. If you can actually notice one more thing, the input voltage and V01 are actually in opposite phase. So that's why it was minus RD by 1 over Gm plus. So we actually wrote this negative now. So this minus can be seen in that out of phase condition. Can you see this is input voltage which is rising, this is the output voltage which is going down. So this is V01. If you actually see V02, let me do V02 here. Can you see V02 is also in the same direction? What I'll do, I'll just put it in different pane. I will put this V02 here. I'll just make it in a different color. See now. If you can carefully notice this V01 and V02, they're actually in the same phase, but both of them are out of phase with the input voltage. Both of them are out of phase with the input voltage, because if you can see in this particular analysis, both V01 by VCM and V02 by VCM had the same expression of minus RD by 1 over Gm plus 2 RSS. Here also it is same, meaning V01 and V02 will have same phase with respect to VCM. So of course they're going to have same phase with respect to each other, but it is out of phase with VCM because of this negative sign. Suppose if I take the differential voltage, so what I'll do now, I will do one more thing. I'll just do the differential voltage. I'll make it V02 minus V01. You can see now I'm doing V02 minus V01. Interestingly, if you see this V02 minus V01, suppose if I put it in different pane, I'll just put it in different pane. See here, this is a perfect zero. I'll just make it different color. Can you see this is a perfect zero? Can you see the output voltage is zero? So that's what we said here. When you are differentially measuring the output voltage, suppose even if you simply consider what is V02 minus V01, shall I say V02 minus V01, what is this? It is actually a gain of a common mode if it is differentially measured multiplied by PCM. Since this is 0, so 0 into anything is 0. So you have the output voltage when it is differentially measured is equal to 0, because gain of the amplifier is 0. Gain of the amplifier is 0. Okay.